Hello everyone. Welcome to our session today. I am so excited to lead you on an incredible journey to the largest and most mysterious world in our solar system, Jupiter, often called the King of Planets. Take a look at this stunning view of the planet. Jupiter is famous for its colorful atmospheric bands and that massive swirling storm known as the Great Red Spot. That storm alone has been raging for hundreds of years and is actually large enough to swallow Earth whole. As a gas giant, Jupiter is made almost entirely of hydrogen and helium. It's so massive that it contains more than twice the mass of all the other planets in our solar system combined. Because it doesn't have a solid surface like Earth, exploring it requires a very special kind of mission. Today, we aren't just going to look at pictures. We are going to conduct a hypothetical mission. A what-if scenario where we imagine falling directly through Jupiter's atmosphere to see what lies beneath those clouds. Our journey will be broken into stages. We'll start by crossing the deadly radiation belts, then we'll navigate the thick clouds, and finally we'll experience the crushing pressure of the deep interior. It's a dangerous path, but a fascinating one. Are you ready to dive in? Our journey into the gas giant begins not with a crash, but with an invisible, lethal barrier. This is stage one, the deadly radiation belts. Long before we reach the colorful clouds we see in telescopes, we have to survive this. The reason these belts exist is Jupiter's massive magnetic field. To put it in perspective, it is 14 times stronger than Earth's. It's the largest structure in the solar system, acting like a giant, invisible magnet. Because the magnetic field is so strong, it acts as a massive particle trap. It captures high-energy particles from the sun and nearby moons, accelerating them to incredible speeds and creating belts of radiation far more intense than anything near Earth. When we talk about human impact, we aren't exaggerating the danger. Without heavy, lead-shielded protection, a human would be fatally irradiated in just a few minutes. This is why our robotic probes, like Juno, have to be built inside armored titanium vaults. Keep this in mind. These dangers exist far before a spacecraft ever touches the atmosphere. In fact, you wouldn't even make it to the top layer of clouds without significant protection. Now that we've cleared the radiation, let's look at what happens when we finally reach the atmosphere. Now that we've braved the radiation belts, we are finally piercing the upper atmosphere. The first 100 kilometers of our descent are truly breathtaking, but incredibly hostile. Our journey begins in the high white ammonia ice clouds. As we drop lower, we transition through layers of ammonium hydrosulfide, which gives Jupiter those distinct brownish-orange hues we see from space. Initially, it is biting cold. We're looking at temperatures around minus 150 degrees Celsius. It's a frozen chemical landscape that would freeze most equipment instantly. And then there's the wind. Notice this value speeds here exceed 600 kilometers per hour. That's more than double the speed of the strongest hurricanes on Earth, tossing our imaginary probe like a leaf. To really feel the scale of this, let's look at a simulation. This POV footage shows the rapid movement through thick cloud decks and the occasional flash of Jovian lightning. Let's watch. Welcome. We're about to dive into the massive atmosphere of Jupiter, the largest planet in our solar system, to see how pressure changes with depth. Use this slider to control your descent. As we go deeper, the weight of the gases above creates immense pressure. At 50 kilometers down, we reach the ammonia clouds. Even here, the environment is already becoming significantly more pressurized than Earth's sea level. Keep a close eye on the depth and pressure readings here. Notice how quickly the numbers climb as we descend further. We have reached 250 kilometers, known as the crush zone. At this depth, the atmospheric pressure is so intense that standard human exploration equipment would be instantly destroyed. Try adjusting the descent rate to see how quickly conditions change. Beyond 500 kilometers, the pressure becomes so great that hydrogen begins to behave like a liquid metal. Following our discussion on the crushing pressures we just experienced, we've now descended to a depth of about 10,000 kilometers. Here, something truly extraordinary happens to the hydrogen that makes up most of the planet. At this immense depth, the pressure is so intense, millions of times greater than Earth's atmosphere, that hydrogen is squeezed into a state that doesn't exist naturally on Earth. It becomes a liquid metal. In this state, it can conduct electricity just like the copper wires in your home. And it's not just the pressure, it's the heat. Temperatures here reach incredible levels, actually exceeding the surface temperature of the Sunday. We're talking about a glowing liquid metallic sea at tens of thousands of degrees. Because this liquid metallic hydrogen is constantly moving and conducting electricity, it acts like a giant generator. This magnetic dynamo is the source of Jupiter's incredibly powerful magnetic field, which we touched on when we discussed the radiation belts earlier. In this environment, the very idea of falling changes. Because the soup is so dense and hot, objects wouldn't fall quickly. They would sink slowly, much like a pebble through thick honey. It's a strange alien world deep beneath the clouds. Next, we'll see what lies even deeper at the very core of the planet. Building on the strange world of metallic hydrogen we just covered, we now reach the final stage of our journey, the heart of the king of planets and the ultimate fate of any object that enters its atmosphere. The descent into Jupiter is essentially a one-way path of total disintegration. As we move deeper, the conditions become unimaginable for any human-made technology. The heat and pressure at these depths are so extreme that they vaporize every material we know of. In fact, most scientific models confirm that a probe would likely be completely consumed by the environment long before it could even get close to the center. If we could somehow survive the trip, we'd reach the core, a dense, rocky, and icy central mass. To give you an idea of its scale, it is estimated to be 10 to 20 times the mass of our entire Earth packed into the very center of this gas giant. So, while Jupiter is visually breathtaking, it truly is a lethal no man's land. Its beauty hides an environment that is fundamentally hostile to exploration. Before we move on to our final project, where you'll try to design a probe for these conditions, let's reflect on this. We have reached the culmination of our journey today. As we just explored on the previous pages, Jupiter's interior is perhaps the most hostile environment in our solar system. Now, it's your turn to apply everything we've covered to design the indestructible probe, a conceptual craft designed to outlast the Galileo mission. In this final capstone project, your team must address the triple threat of radiation, crushing pressure, and intense heat. You will need to propose specific material solutions and outline a mission plan for data transmission from the deep interior. Take a moment to look at the available roles from engineering lead to mission specialist and select the one that interests you most. Once you're ready, let's see if we can build something that truly survives the King of Planets. This will be a fantastic way to conclude our session.